Hey guys, how's it going? Fishing in space here. Today's video is about probability. Why probability theory doesn't work. Or deconstructing probability theory. So to start off, I'm going to make a claim that's going to sound pretty bold. And I'm going to explain that, and I think by the end of the video, you'll at least be questioning, and you might even agree with the claim. So, we're going to take the example of a coin toss. It's the simplest and probably the most widely used to explain probability theory or to test it, and because it offers a 50-50 chance. Probability theory will say you have two results, 0 and 1. It's either 0 or it's 1, meaning it's either heads or it's tails. So if probability theory is real, every time you make a coin toss, it's always going to land on its side. And so now I'm going to deconstruct probability theory and prove and show you why it's false. So let's start with this. You have a coin, and we're going to take this coin and we're going to set it with heads facing up, just for this example. I know you can't really see, but heads facing up. And I'm going to flip this coin in such a way that it only rotates once in midair. Flip it, rotates once. It's going to land on tails. Every single time you start with heads and flip it once and land, you're going to land on tails. Probability theory would dictate that 50% of the time, it's actually going to land on heads, despite you starting on heads, flipping it in a way that rotates it once, and landing on tails. Probability theory will say that that's 50% of the time it's going to land back on heads. Now, that doesn't make a whole lot of sense, and you'll say, well, probability, it obviously doesn't work if you have a control. If you know if you control the coin toss, you invalidate the probability of what's going to happen. You know the answer already, and that's true. So let's say you flip the coin in such a way where it rotates twice, still starting on heads. Well, you're going to rotate it twice, you're going to get back to heads. And so from that, we know that every even number of rotations is going to land back where it started in this example, or to keep things simple, it's heads. So every even number of rotations is heads. Every odd number is going to land on tails. If you flip the coin and you get a 34 rotations, it's going to land on heads again. Let's say next time you do 25 rotations, it's going to be tails. Probability theory would say this is, and you're going to start seeing it break down from here, the entire mathematical probability theory. If I flip this with 34 rotations starting on heads, there should be a 50% chance that it still lands on tails, right? That would be probability theory working, or that's how probability theory would explain it. This obviously doesn't work. It doesn't make sense. It's obviously going to land on heads if I flip it an even number of times. So probability theory only works if you are ignorant of the method or the factors that contribute to the tossing of a coin. If you know how many times the coin is flipped, then you're obviously going to know the result of the coin toss, which is true. So if I flip it and it rotates once, probability theory doesn't apply to that. Keeping in mind that that's still a coin toss and should fall under probability. So every time I flip it, even if I do a random number of rotations each time, I could still tangibly observe what the result is going to be before it lands on the ground. Perhaps not with our eyesight or with our physical, biological capabilities. If you were friends with a dragonfly, perhaps you could ask him what the result is going to be as they see in a higher, or they see more frames per second than we do. they could see the coin rotating in a very individual sense, not as a blur. And they could tell you, hey, it's rotating an even number of times. The coin started on heads. It's going to stay heads. We could also do this with high-speed cameras, obviously. So since probability theory only works if you don't know what's happening, sounds quite like the most unmathematical and unscientific process I've ever heard. Here we have a field that depends upon consistency, on what you can observe and quantify and test. So the very fact that probability theory innately needs its observer to not understand the inner workings of a coin flip is, I think, a red flag in the entire theory. Perhaps it should be called postulation theory and not probability theory. So long as you don't know the result of a coin toss, it will appear random to you. There's no room for probability theory when you know the result of the coin toss before it happens. And this is something you could reasonably know before every coin toss. Let's say your vision or senses were so heightened that you knew the amount of force someone was going to apply to their coin toss. You knew the air resistance, the weight distribution of the coin, and the method or the catch or the way the coin is going to land. And so every time you watch the coin toss, maybe you call it in the air, maybe you predict before, you can get it right every single time. So this goes back to a one rotation coin toss. If you know the amount of rotations a coin is going to have, probability theory is thrown out the window. This is a mathematical and scientific theory that has huge implications for a lot of different fields. It's a mathematical field of study that relies on your lack of observation, which doesn't very much make sense. Here's an example. Okay, so let's say you have a machine with a specific power output that is not going to change through the duration of this experiment. You place the coin on the same spot, same kind of coin. There's no air resistance. The coin is going to flip in the air the exact same way every single time, given a perfectly controlled experiment. If I set the robot to always flip heads, it's going to flip heads every single time. Probability theory says that 50% of the time, tails is going to be the result. Maybe another example will help form this sort of idea in your mind. Let's say you have a roommate in an apartment, and one day you're coming home to the apartment from work or something, and you're with a friend, and you tell your friend, hey, there's a 50% chance that when I open this door, my roommate is going to be inside of my apartment. My friend is like, okay, let's go inside the room. So you open the door, look in the apartment, and he's not there. So obviously there were two results. He's either there or he wasn't there. 50-50 chance that he would be there when you got home. You open the door, you go in the building, and your roommate's not there. So let's say during the same span of time, you walk back out the door, close the door, and say, there's a 50-50 chance my roommate is going to be in the apartment. And so you open up the door again, and you look back inside the apartment. He's still not there. There's a 50-50 chance that he was going to be there, but he wasn't there again. And you could do this, let's say, 1,000 times. And so you keep opening and closing the door, looking for your roommate in your apartment. Every single time he's not in there. So I guess to reiterate the idea, or to highlight the point of that example, is probability theory doesn't work if you know the result, right? But every single thing probability theory tests, you are able to know the result if you understand the process. Probability theory needs you to not understand the process for it to make sense, and even within its own realm of mathematics, it doesn't make sense. You have to not know anything about the process of whatever you're of whatever probability you're testing. Since we should rename it to postulation theory, because you're only allowed to have an idea of the answer. You're only allowed to know so much that it's either heads or tails. You can't know anything else about the coin toss for probability to work. And that's why I use the word postulation as a better description for it. So you can then again apply this to random number generators, or RNGs, a computer generated result or number. Now that obviously is a little bit harder to know what the answer is going to be, but this was a programmed code with an algorithm. You could figure out the algorithm, you could reverse engineer the code, and you could figure out what each answer is going to be. Even because a computer generated number had to be made by someone, the same way that a coin toss is flipped by something, or that a chance meeting isn't chance meeting at all. It is this person was going in this place and that person was also going to that place, and so you run into each other. It's not that there was a 0.5% chance that you two would meet. It's that you were both going to this place, so you're guaranteed to meet because you're crossing paths. And I believe this is the percentage, but out of 1,000 coin tosses, for you to obtain the average, which is 50-50, 50% heads, 50% tails, 500 heads, 500 tails in the case of 1,000 coin tosses, for you to reach the average number that probability theory proposes for a heads and tails coin toss is about, I believe it's 2.5% chance of actually hitting the average. It's almost harder to actually hit the average probable number than it is to go over or under that number. So let's go back to the single coin flip, or you could go back to the machine coin flip. Either way, the result is guaranteed. You have a controlled experiment where you know what the result of the coin flip is going to be before you flip it. If probability theory were correct, you have a 50% chance that it's going to land on heads and a 50% chance it's going to land on tails. Which, if you know the result is going to be a tails because you started with heads and you're going to flip it an odd number of times, what's going to happen is if you have an even split of how it's going to result in, despite the fact that an odd number would result in a tails, it's going to land on its side because there's a 50% chance, no matter how controlled the coin toss is, that it's going to land one way or the other. Because of this, you're going to always land on the side because it's perfectly random. It's perfectly evenly split to land one way or the other if probability theory is correct. If probability theory is incorrect, then probability doesn't work when you know the answer to something. In this case, I know the answer to the coin toss, and I could reasonably find the answer to every single coin toss ever. Maybe not with my current biology, but perhaps if I had slightly better eyes, I could see the result of a coin toss in midair, see every individual flip, count them on the way down, and tell you the result of it before it happens. And you say, okay, well, this isn't going to be a toss in the air coin flip. It's going to be, you have to predict it before. Well, before you flip it, I could see the, let's say I could see your muscles and I could see the neurons and I could tell you how much energy and output force you're going to put on the whatever location of the coin you're going to flip from. And I could tell you, okay, when you're flipping it like this and you're using so much pounds of force, it's going to flip an even number of times. I know you have heads face up. It's going to be heads again. So the results are tangible no matter what activity of betting or gambling or probability, guessing, luck, randomness, anything that has to do with those are entirely knowable, predictable, reasonably. You could determine how it's going to happen. When you know what the result is, probability theory doesn't work. And you are able to know the result of anything. Probably not going to know how a particular slot machine works, but you could learn how that slot machine works. You could learn all the gears and the computer numbers and all the inner workings of the slot machine, and you could find out, well, this slot machine only wins once every 300 plays. And then you would know not to play the game until you're the 300th player. So the house always walks away with more money in a gambling casino or gambling building because there isn't a probability theory. If everyone went into a building knowing the results of every single game, and let's say this building is a coin toss game, you put money on what you think the result of a coin toss will be, and then you make that amount of money, just for simplicity's sake. Since the results of a coin toss are verifiable as they're happening, before they're happening, or after they happen, whenever you have to place your gamble or give your answer. Probability theory applied, if it was real or worked, no one would ever make money gambling. It's because probability theory doesn't work that gamblers are able to make money, or the house is able to profit. Because if you truly had a 50-50 chance of anything in a coin toss, gambling in a coin toss, you would know that if you played 10 games, you would always go home with the amount of money you came in with, assuming each gamble was the same amount of money. If you bet $10 every single game for 10 coin tosses, you would end up with a profit of $0. You wouldn't end with negative or positive earnings. But it's because probability theory doesn't work that you can lose $100. You could make $100 out of 10 coin tosses. But then keep in mind, you can know every single coin toss. If you go gambling knowing how everything works, you'll know every single time what the result will be. Probability theory would be, you would never be able to win, because even when you know the answer is going to be heads, there's a 50% chance it won't with probability theory. And that's why the whole mathematical theory just deconstructs and folds in on itself, because it relies on you not knowing something that you are able to know, which, if you are able to know the answer, it's therefore controlled, and probability theory doesn't apply, which essentially means that you know the answer, and it's no longer an equation. There's no longer a percentage chance, or there's no odds to it. So yeah, I think I got my point across. It's a bit hard to explain, but I think if you do the experiment or toss coins yourself, you'll notice, especially the higher you go, you'll never get the average number of coin tosses. If every single coin toss is a 50-50 chance, you getting 5 heads in a row is not any less of a chance of you getting 3 heads and 2 tails, or 1 head and 4 tails. That it's always a 50-50 chance, and there's no way of ever knowing which coin toss you'll get. The odds of you getting a specific pattern of coin tosses, which should be 50-50 no matter what if probability theory were correct, but it recognizes its own inconsistency, and so creates a declining percentage. So if you flip 10 coins, or a coin 10 times, and you get heads 9 times, probability theory dictates you have a 10% chance of getting heads again, and therefore a 90% chance of getting tails. Well, let's say on that last toss you make it only you make it a 2 rotation toss, heads facing up from the start. You rotate it twice and it lands on heads again. Well, you just had a 90% chance of getting tails for that very last coin toss. and you got heads again because you knew the rotation, and you can always know the rotation. And probability theory just collapses on itself without, too much effort. You can make this simple observation yourself. You're never going to get the probability that the theory purports. So yeah, I think I'll just leave off that final note. So I guess that's the video. Ended kind of abruptly, but peace out.